Hola clase. Today we're going to go through the proof of DeMoivre's theorem, which allows us to do exponents of complex numbers. Now, for us to get this one, there are a couple of things that we need to know. First of all, we need to know complex numbers in polar form. So remember that they've got a modulus and an argument. Then you need to know how to multiply complex numbers in polar form. And then you need to know what a proof by induction is. So in layman terms, it's a matter of finding a pattern, or if you want to see it that way, if I find that something works for specific cases, then from here I can see the pattern and see that it works for a general case. Because this is what we're going to do to solve it or to prove it. We're going to do a proof by induction. Okay, we're going to start with something that we know, which is how to multiply two numbers if they are in polar forms. So we know that to do that, we simply multiply the moduli and then add the arguments. But now for this theorem, we're only going to use one number that has its own modulus and its argument. And from there, I can start getting exponents of it. I could say, not that we would ever write it that way, that z is z to the power of 1. And that is that r c's of a. Well, this is true, so I can come from there and do z squared, which could be z times z. And that could be r times r, c's of a plus a. And because now I've got terms that I can simplify, that would be r squared, c's of 2a. Now combining these two things, z and z squared, I could repeat the process and try to get z cubed, which, yes, could be z times z times z, or z times z squared. If we do that, that could give me r times r squared, c's of a plus 2a. And then we can simplify it. So let's see if I can do it sort of in a column. That could give me a cube, c's of 3a. Now repeating the same idea, I could get z quartic, which of course could be z times z times z times z, or z times z cubed. So of course could be r times r cubed, c's of a plus 3a, and when we simplify that, it would give us r to the power of 4, c's of 4a. And we're beginning to see a pattern there. I could do the same for z to the power of 5, 6, and so on. I can do the same for any number that z to the power of n. Doesn't matter which n, it could always be z times z to the power of n minus 1. And eventually I would be able to get to there. So I know how this one is going to look. It would be r times r to the power of n minus 1, c's of a plus n minus 1a. And this I can simplify. That would give me r to the power of n, c's of n times a. So I can come here and get my theorem. I'm telling you, okay, if I've got a number in polar form that has a modulus and an argument, then that number to the power of n is the modulus to the power of n cis of na. And this is my theorem proved by induction. This is a very quick way of doing exponents in complex numbers, but it's also going to be very handy for actually solving complex roots. And for that there will be a video, and it will be somewhere up there, but it will be coming soon. The important thing is that now we know it and it's ready to be used. So now it's your turn to go and practice. Thanks for watching.